This lecture's this lecture is going to continue our study of intermolecular forces of attraction. And before you watch this lecture, please go in and complete or attempt to start the in-class worksheet, IMFs and boiling points. There's a link on Canvas. This will work best if you try and complete this on your own and then watch this lecture where we're going to go through this worksheet. And so the first part of this worksheet has to do with LDFs, London dispersion forces, and boiling points. So again, complete part one of the activity, pause the video, and then come back. So the first part of this worksheet has to do with the group 14 hydrides, where what we're doing is we're changing CH4, SiH4, GeH4, and SNH4. And if you look on the periodic table, what you see is these are all carbon, silicon, germanium, and tin. They're just going down a group, 4 hydrogens attached. And so when we look at these molecules, we should see 4 things attached to a central point. They're all tetrahedral in structure. They're also all non-polar because all of these bonds are non-polar, but also they're perfectly symmetrical. So they're all non-polar molecules. At that point, we should identify that the only IMFs present are London dispersion forces. So when we look at that, we could say, okay, these have London dispersion forces because all molecules have London dispersion forces. And so we can then say what is going to have the highest boiling point here, and we're given some data, and the data shows that the boiling point, all right, so the boiling point increases as we go from CH4, SiH4, GeH4, and SNH4. And what must be happening is if the boiling point is going up, it's becoming much harder to separate these molecules. So remember, a boiling point is really a measure of how strongly do molecules of the same type stick together. So if you only have methane, how much energy do you have to put in to turn methane liquid into methane gas? And we have to put in energy because all of the liquid molecules are attracted to each other. So we have to overcome that force of attraction. And what we're seeing here is it takes more energy to separate tin hydride than it does methane. So why is that? The only intermolecular force of attraction present in these are London dispersion forces. So we're seeing that the order of strength of London dispersion forces, CH4 is the weakest and SNH4 is the highest. And so what we can do is we can make a correlation and we can say whenever you're comparing molecules, the molecules with the most total number of electrons, not valence, but total number of electrons, will have the highest London dispersion forces. Okay, so we can use that to sort of predict which molecules will have a greater London dispersion force. In the next problem on the worksheet, you're giving a picture of a chart of hydrocarbons and their boiling point, and has to explain that. And so this is showing the same thing in a different form, but what it's comparing is methane, CH4, ethane, CH3, and hexane, which again is a hydrocarbon only made up of carbon and hydrogen. It's 6 carbon long chain, right, with hydrogens all around. So these are all non-polar molecules. So again, they only can form London dispersion forces. They can't do anything else. So what we do is we predict that hexanes is going to have the largest boiling point of this bunch. Why? Because it has the strongest London dispersion forces. How do we know it has the strongest London dispersion forces? Because it has the most electrons. One other example of the same thing is we can predict the boiling point trend for the noble gases. So if we look at group 18 on the periodic table, we can say which of these will have the highest boiling point and why. And again, if you're looking at the noble gases, these are molecules that can only form London dispersion forces. And so what we see, we can look at a table to back this up, that the order of boiling points goes from helium, neon to argon, krypton, xenon to radium, going all the way down. And so what we see is the order of the boiling point correlates again with the number of electrons. Right, as we go down the periodic table, these get bigger, more electrons, boiling point goes up. Right. So again, the key here is that stronger LDFs with more electrons, total electrons. So we can then go on to part 2 of our lecture. And in part 2, we're going to look at a series of molecules. In this case, we're looking at HCl, HBr, and HI. And we're going to sort of tease out, and can we explain the boiling point trend here? And as we look at these, the first thing we should ask ourselves is what intermolecular forces of attraction are present in these molecules. And so we can look at them and say HCl, HBr, and HI are linear molecules, and they are all polar. Okay. Further, we know from our electronegativity that HCl is the most polar of these three because chlorine is the most electronegative, then HBr, and then HI. So HCl is the strongest dipole-dipole, then HBr, and then HI. However, when we look at the boiling point trend, HCl is the lowest boiling point. This means that HCl has we can say this has the weakest IMFs, but it has the strongest dipole. So why is that? How come HI, which has to have, because of where it is, the strongest IMFs, because it has the highest boiling point, so it's the strongest IMFs. So how can we explain that? We can't do it with dipole-dipole because HCl is the strongest dipole. So what is happening here is that we're seeing that LDFs must be stronger than dipole-dipoles because HI is the most electrons, so this has the strongest LDFs. And the key point here is what's in the box down below. Whenever we think about this, London dispersion forces are actually stronger than dipole-dipole forces. And when we think about this, we can start to compare other molecules. So for example, if we look at something like HBr and GEH4, so if you compare these two molecules, HBr and GEH4, we can see these have, we come down here to the x-axis, these have the same number of electrons. So what we're saying is that LDFs here are equal. So they have roughly the same LDFs, but HBr has a higher boiling point than GEH4 because HBr is also polar. So the key is they have the same LDFs, but this also has dipoles. And it's the presence of the dipole in addition to the LDFs, which is going to give this the higher boiling point. So you can kind of think about dipole-dipoles as being tiebreakers, right? So they have the same LDFs, but HBr also has dipoles, so it's going to have the higher boiling point. So let's look at a little bit of review. A typical type of problem related to this would be like this one, where you're given 3 molecules and you're asked to rank from lowest to highest the boiling point. So which of these has the highest boiling point, which of these has the lowest boiling point. And given a problem like this, the first thing we want to do is determine the intermolecular forces present in each. So determine the total number of electrons in each molecule, draw their Lewis structures. All right, so 36 electrons, 36 electrons, 54 total electrons. Then we're going to say we're going to then compare the London dispersion forces and say this tin hydride is going to have the highest boiling point because it has the most electrons. It's more than GeH4 HBr. So this is our highest boiling of the three. Then based on LDFs, these are the same, but as we just discussed, HBr is also polar, so that's going to be number 2, and GeH4 would have the lowest boiling point or the weakest intermolecular forces of attraction. Okay, so now let's move on to part 3 of this activity. So again, if you haven't done it yet, pause the video, go complete the activity, and then let's think about it. And in part 3, we can see the full plot of all these different series, different groups of their hydrides, boiling points, and number of electrons per molecule. So we've looked at this blue series, and we looked at the black series as well. When we look at these now a little bit closer, one of the interesting things is there's these 3 molecules that don't fall with their series, right? Take water, for example. If we were to extrapolate this red line in water, we should expect water to be about here. HF, if we extrapolate the line, should be about here. And NH3, if we extrapolate the line, should be here. So we should be predicting boiling points in this range, and instead they're way up here. Now notice this difference. Water boils at 100 degrees Celsius. But here, if we follow this plot, we should predict about like negative 80. Think about the difference for life. If water boiled at negative 80 degrees Celsius, there would be no life because our bodies would just boil away and turn into gases. Life could not exist except for the fact that water boils at 100 degrees, and so it's a liquid at room temperature. But why is it? Why do these 3 molecules have such a high boiling point? What's the difference between these? And the key for this is these 3 molecules can form hydrogen bonds, right? They are the only molecules on this chart that can form a hydrogen bond. And so when we think about intermolecular forces of attraction, the strongest intermolecular force of attraction are hydrogen bonds, then the LDFs, and then dipole-dipole. And we see hydrogen bonding is much, much stronger than the other 2, although all of them are still much, much, much weaker than a covalent bond. Okay, so it's the presence of this hydrogen bond that's making it so hard to separate these molecules and giving rise to their increased boiling point. Now, when we look at this a little bit closer, we might ask the question, why is water so much higher than HF and NH3? All 3 can form hydrogen bonds, so why does water get so much more of a boost as compared to HF or NH3? Right? They all have the same LDFs. In terms of polarity, HF would have the most dipole-dipole, so what's going on here? And what's happening is coming back to structure, and oftentimes people refer to water as the perfect hydrogen bonder. And the reason for that is in order for a hydrogen bond, recall, you need a lone pair of electrons that's attached to nitrogen, oxygen, or fluorine, and you need a hydrogen attached to nitrogen, oxygen, or fluorine. So each water molecule has 2 lone pairs and 2 hydrogens. This allows water to form an infinitely numbered hydrogen bonded network, right? This can just hydrogen bond to infinity with as many water molecules as there are. Both NH3 and HF have either 3 hydrogens in 1 lone pair or 3 lone pairs in 1 hydrogen. So within ammonia, if you have a bottle of ammonia and you imagine all these ammonia molecules, eventually you run out of lone pairs to hydrogen bond because you have too many hydrogens and not enough lone pairs. And the opposite is true for HF. you have too many lone pairs and not enough hydrogens. So it's this 2-to-2 ratio that makes water the perfect hydrogen bonder, making it the highest boiling point. Thank you.